Hey guys, and welcome to our quadratics example video. So here we're going to work two problems, and both of these problems will incorporate a lot of different aspects of working with quadratics. Okay, so the first problem we're going to deal with is we are given a graph, and I want to go from this graph to a symbolic form of the function. Now, if we remember our forms of a function, we have our standard form, which looks like ax squared plus bx plus c. We have our vertex form, which looks like a times the quantity x minus h squared plus k. And lastly, we have our factored form, which is a times the quantity x minus r times the quantity x minus s. Now, depending on what you're given in the graph, you're going to choose whichever form works best. Now, looking at this graph, I chose this one very specifically because it gives us a lot of things really easily. It gives us our vertex. It happens at the point negative or 1, negative 4. And it gives us our two zeros, negative 1, 0, and 3, 0. So because we have both of those, we could really go either way with either using our vertex form or our factored form. I want to start out using our vertex form first, and then we'll do our factored form in just a minute, okay? Now, what we need, no matter what, if we do in vertex form, we need to know the vertex, and then we need to know at least one other point. If we're doing factored form, we need to know our factors, or our zeros, and then we need to know at least one other point. The reason we need that one other point is because we need it to be able to calculate our a value, and you're going to see why in just a minute. So, we look at this vertex. So we want to go vertex form. So, this is what we're trying to fill in. Now, if we remember, right, HK is the coordinates of the vertex, which means that's my H and that's my K. What's really nice is I can just plug those right into our function. So this now becomes A times X minus H, which is 1. So it's going to be minus 1 plus K. So K is negative 4. So instead of plus negative 4, we just say minus 4. Cool. The problem is now, how do I find this A? Right? And this is where that other point comes in. Because just like if you think back to linear functions, right? Once we had 2 points, right? Once we used those and found the slope using our slope formula, we plugged one of those points in to find our y-intercept. Here it's very similar. We use the point that we need, that we know, so in this case our vertex, to fill in our h and k value. Or in a minute we'll do it with the roots, and you'd use those to fill in your r and your s values. And you need one more point to be able to create an equation that gives you a. Now some of you might ask, why can't I use the vertex, plug that in? Well, let's see what, if I plug that in, that means x is 1. So we have 1 minus 1, 0. 0 squared is 0. 0 times a is 0, so that a goes away. So it doesn't help us to solve it. So just for the sake of not having negatives, if we don't have to, I'm going to use this point here, 3, 0. So remember, this point being on this function means that when x is 3, f of x is 0. So the equation I get is 0 equals a times 3 minus 1 squared minus 4. Okay, so the only thing I did is I replaced the x value with the x value of the point that I had, and I replaced the f of x, or the output of the function, with the output at that point. Now I just have this nice simple equation. We can solve it, right? So we just go through and evaluate what we can, simplify things, and then we're going to go through our algebra solving process. First thing, what is 3 minus 1? Well, 3 minus 1 gives me 2. 2 squared minus 4. Now, this is a pretty easy function. I give it to you, right? But the process is the exact same. And so some of you may see this and get to a point and be like, oh, I know what to do now. Don't skip ahead. Just keep watching. That way, if you get to a point where you struggle later, you can come back and kind of rely on this knowledge. The next thing we want to do is just simplify this 2 squared. So we get 0 equals a times 4 minus 4. Now, especially at this point, some of you guys are going like, I know what a is, and that's great. But let's follow through the solving process. So to solve for a, I have a times 4 minus 4. That's the same as 4a minus 4, right? So what we have to do is we have to add 4 to both sides to get rid of that. when I do, I get 4 equals 4a, because a times 4 is the same as 4 times a. And then we divide both sides by 4, and I get a equals 1. Awesome. So that means I can get back up here, and there's 2 ways. Since a is 1, we could just write 1 times all the stuff, but we know 1 times anything doesn't do anything, so we could just, right? And the reason we can do that is simply only because a is 1. So I'm just going to write it in there just so it's not confusing, but if you're comfortable with that, feel free to drop that. And there we go. We have our vertex form. So we know what this is supposed to look like. It's easy. Now what's really cool is I know what my a is, right? So now I know what my a is in every other form. I don't have to do all that much work. So now I'm going to erase this stuff here. And I want to convert this to standard form. Now, standard form is ax squared plus bx plus c. I'm going to use the fact that we already know our a value. So I know standard form I have 1 x squared plus bx. Now before I write plus c, I'm going to ask, right, standard form, every form gave us a different piece of information about the function. What did standard form tell us? Think about it for a second. If you want to pause it and look it up, figure it out, do it, pause it now. All right. Standard form tells us the y-intercept. The y-intercept is at the point 0, comma, c. Well, if we look at this graph, this passes through 0, negative 3. So that tells me that c has to be negative 3. Bam. Now the only thing left to do is find b. Now, you might be wondering, hey, wait, we were going from vertex form to standard form. We've multiplied that out in the past. That's what we did. And that absolutely works perfectly fine. I'm just kind of showing you another way, using the graph to kind of do what we have, use what we have. And then, now I have another equation with one unknown. We did the exact same thing we did with our vertex form to find a. And to find b, I'm just going to plug in this point here. This idea of getting an equation down to where you have one unknown value and then plugging in a point is something that we're going to see come up a lot this term. So we are down to having one unknown value. We know what our a is. We know what our c is. X is our variable. We don't know what b is. So to find b, I'm going to use this point, 3, 0. And we could use any of these points, but 3, 0 is a nice one to work with. Since 1 times x squared is just x squared, I'm dropping that 1 now. So remember, when we're plugging this point in, we set our function, our set equation equal to the output, 0. And then we replace all of our inputs, our x's, with 3. So I get 3 squared plus b times 3 minus 3. Now I just want to go along the process of simplifying. 3 squared gives me 9 plus, now b times 3 is just 3b minus 3, still not 0. Now 9 minus 3, we get 6 plus 3b. Now I need to subtract 6. Because we've got that all simplified, so we get negative 6 equals 3b. And then we divide by 3. Those cancel out. And we get b equals, so negative 6 divided by 3 gives me negative 2. So that means that my final function, or my standard form of this function, if we were to have taken this and multiplied it out, would be x squared minus 2x minus 3. Okay, that is the equation in standard form. All right. Now, let's talk about factored form. Factored form, right? We're looking for our roots. So what we're looking for in general, actually I'm going to erase this too. Give myself a little more room. We're looking for a times x minus r times x minus s. Our r and our s value are simply the x values of our zeros, or roots, or x-intercepts. So this is a, times x minus negative 1. So when we subtract negative 1, that's just plus 1. And then we get x minus 3. And so what's really kind of nice thing here to kind of look at is kind of not just how we got from these zeros to these factors, but from these factors to these zeros. There's just a really kind of easy, simple sign swap idea, or what we're really asking is, what does x need to be so that x plus 1 is 0? Well, x needs to be negative 1, because negative 1 plus 1 equals 0, and that's our factor, our root. Okay? So, right now we're at a very similar place that we were in the vertex form. We just need to figure out what this a value is. Now again, I already know we already know it, but I want to act like we don't. Okay? And we can't use either of these 2 points because they just make the whole thing equal 0 and the a goes away. So we can use the vertex here that we know, right? And let's say we didn't know what that was the vertex. We were just given, say, a list of points or whatever, or we had a different point. Either way, it all works the exact same way. We simply create a new equation. So the output of my function is negative 4. So we have negative 4 equals a times, and the input is 1. So this is going to be 1 plus 1 times 1 minus 3. Okay, so now we want to go through and simplify. 1 plus 1 is 2, and 1 minus 3 is negative 2. We're going to simplify one more time where we have 2 times negative 2, and that's going to give me negative 4. Lastly, we just divide both sides by negative 4, and we get a equals 1. And then you just restate your final answer, right? Our factored form of this function is equal to 1 times x plus 1 times x minus 3. There you go, guys. That's it. That is the way we go from a graph to an equation, no matter which form we're dealing with. We very rarely, and if by rarely I mean I will never ask you to do it, ask you to go straight from a graph to the standard form. I will usually ask you to go from the graph to vertex or graph to factored, and then I may ask you to give me the standard form, which is just asking you to multiply that out. If you forget about multiplying out, just go back and watch the last video. All right, so there's a couple other questions I want to ask you based on this graph. Okay, what's the domain of this graph? So what is the domain of this function? Remember, domain is the set of all inputs that are valid and meaningful. Valid means if I put something in, I get something out. Meaningful means it makes sense in the context. There's no context here. Don't have to worry about meaningful. I just have to worry about a valid input. Remember, inputs are on our horizontal axis. And since we see these arrows, what we can assume is that this graph is going to continue on in the same pattern forever. Which means any number I pick all the way out here, I erased the negative. No matter what I pick, I'm always going to be able to go up and find a point. Similarly out here. So that means very simply our domain is negative infinity to infinity. That's it. Now what about our range? Our range is the set of all corresponding outputs, right? So outputs, those are on our vertical axis. We think kind of similar. We're just kind of think, okay, is there any number I can pick that I kind of can go left and right and won't ever hit my function? Well, we have 5 questions to help guide us with these. Remember, if you don't remember them, go back and watch some of the earlier videos. So our 5 questions are, can it be negative? Can it be all negatives? Can it be 0? Can it be 1? Can it be positive? Can it be all positives? So we ask yourself those questions. Remember, we're talking about range, so we're talking about the outputs. So can the outputs be negative? Yeah, right? We see this point here is 1, negative 4. Right? And here's negative 3, right? There's negative outputs. But can it be all negative outputs? Right? We can see if I do negative 5, there's no input of this function that gives me a point at negative 5. So I can't be all negative outputs. So I need to figure out what's the lowest negative output I can be. And if we look at this graph, it comes down to the vertex, and that's where it hits and turns back up. And that was at an output of negative 4. So that means our lowest value is negative 4. So our range is going to start at negative 4. But we have to ask ourselves, does it include that point, or does it not include that point? And very simply, because it's the vertex that's included, it includes it. Since it's included, we use brackets. Now, those are the first two questions. Next question, can it be 0? Absolutely. Can it be positives? Yup. Can it be all positives? Since those arrows are going up? Yes. Which means very simply, it goes off to infinity. That's it. There's our domain and range. Nice and easy. Now, two more questions I want to ask with this, and that is simply increasing and decreasing. When is this increasing? When is it decreasing? When we're talking about whether a function is increasing or decreasing, where these things are happening at, what we're asking about is for what x values does the function do this? So the first thing we have to figure out is what does it mean to increase and decrease? Very simply, as you move from left to right, if the function's going up, it's increasing. As you move from left to right, if the function's going down, it's decreasing. So as we look at this graph, you can see that when we kind of first come up to it, it is going down. So it's decreasing from negative infinity, and then the point where it stops is at the vertex, which has an input of 1. So it's decreasing from negative infinity to 1. And increasing and decreasing always gets parentheses. It's something I never mentioned earlier, but I want to mention now. Increasing and decreasing, always parentheses. So if it is decreasing from negative infinity to 1, that doesn't necessarily mean it's increasing the rest of the time, but in this function, it is. So, and if we look at it, right, at 1, at that vertex, it starts increasing, and it increases forever. So then it's increasing simply from 1 to infinity. And there you have it. Easy, nice, simple things. Reading a graph, the ability to look at a graph and pull information from that. Things like increasing, decreasing, domains and ranges, intercepts, roots, things like that is really an important skill. So if that's something you're struggling with, if you don't understand what I just talked about, send me a message. We'll connect. We'll make sure we understand.